Hey guys, and welcome back. So I actually just finished editing all the footage you're about to see, and I want to give you a quick overview and quick recap of exactly what this video is going to be about, because it is a bit of a longer video than I typically post. So this video and this tutorial is about time complexity and BigO notation. Now, I don't focus tremendously on exactly how to write BigO notation and go super in depth, but my main goal is to give you guys kind of a fundamental understanding so that you can use that knowledge to apply it to your own programming and your own code. A lot of people aren't aware of the effects that their programming and the scripts that they're writing have on their code and how slow it could possibly be running. So in this video, what we do is the first 15-20 minutes, we kind of go through and talk about what is BigO notation, how it works, quick summary, and then we actually get into a bunch of algorithms that I've wrote and we analyze them and see how fast or how slow they are. This should hopefully allow you to write better code, faster code, and if you don't know this, obviously you're going to learn. So this is a really fundamental skill. If you're in any kind of computer science field or a programmer in general, it's something you definitely should know. And if you don't, I highly encourage you to watch through the entire video and make sure that you actually understand everything that I'm talking about. So with that being said, let's get into the video. Before I get too far into the content, I'd like to announce that I'm actually partnering with Microsoft and they're sponsoring this video for me to talk to you guys about a new project they've started called the Microsoft Dev Collective. Now, this is a really exciting and great opportunity for you guys, and essentially the Microsoft Dev Collective is a community of developers where you can go to learn and collaborate. Right now, by just simply signing up and becoming a part of the Dev Collective, you're going to gain access to over 30 free courses. That's right, completely free. You don't have to pay for anything. There's a link in the description, and if you go there, it's going to bring you to a page that has a bunch of courses that look just like this. Let me show you. Okay guys, so I'm on the Microsoft Dev Collective website here. I'm just going to click on Explore Learning and have a look at all of the different courses that they have to offer as of now. So like I mentioned, this is a brand new thing and there's going to be new content added on here monthly. So make sure you guys are continually having a look at this, because since the first time I looked at it, there's been some new courses and I know that they're adding a lot of different content that's going to be super valuable. So I just signed in here so I can gain access to all these courses, but essentially I'm going to go to topics and just go to languages, and this is where my tutorial will be showing up. And essentially you can have a look at just some of the stuff they have, like programming foundations, object-oriented design, make your C# code more functional, just a ton of awesome resources. And I know if you guys have a look at here, you're probably going to find something that interests you, and it's free. So what's the harm in having a look at it and checking it out? So anyways, that's been it for this little ad thing. I hope you guys did listen to this and I hope you're going to get some value from this. And now on to the video. Okay, so what this tutorial is really going to focus on is time complexity and BigO notation. Now, I'm not trying to make you guys pros in this, but I really want by the end of this video that you guys are going to be able to look at certain algorithms, maybe something that looks like this, analyze them, and get some kind of idea of how long it's going to take for them to run. Now, this is a really important skill. It's taught a lot in computer science in general. I don't really care if you guys know how to do like big O of n or n squared or like n+1. I just want practically you would be able to look at an algorithm and be like, okay, so like based on my knowledge of kind of time complexity and how things work, this is going to take a long time to run. And the reason why that's really important is because when you guys are writing code, I see it a lot with beginners. They have no idea about how long it actually takes for something to run. And if you're trying to run things on like thousands and thousands of lines of input or this massive I don't know, like text files or something like that, and you have a really inefficient algorithm or inefficient code, it's going to take forever and it might not even run. So I just want you to be conscious of the fact that your code really has an effect on how long it takes for the computer to execute something, and typically the faster something is, the better. Now we're going to talk about a bunch of different algorithms here that I've personally just wrote myself. Some of them are like very well known, but I've just created a few. And I'm going to be doing this in JavaScript, but it doesn't really matter if you don't know JavaScript, because this is just, I'm not going to be writing any code. We're just going to be analyzing it. So as long as you can kind of get an idea of what this code is doing and you've programmed before, you're going to have no problem following along with this if you don't know JavaScript. Okay, so with that being said, let's get started and let's talk about BigO notation and time complexity. Okay, so what is BigO notation? Well, BigO notation, why is this not drawing? Oh, I'm on the eraser, that's why. BigO notation is essentially just a fancy word or fancy notation for denoting how long it takes for a certain algorithm to run. So I've already said algorithm like 100 times, but that's what we're going to be focusing on, algorithms. Now, what is an algorithm? Essentially, an algorithm is a set of instructions, and typically in computers, based on some input, it takes like a certain amount of time to execute. And that's what we're really going to be focusing on here. So algorithms, set of instructions, BigO notations. how long does it take this set of instructions to run based on some kind of input. So what we're mainly focusing on here is input, okay? So, and specifically input size, and then that's going to be related to time. So based on some kind of input size, how much time can we relatively expect this algorithm to take? Now, I'm not saying we're going to measure it in seconds. We're actually just going to measure it in like relative operations. And what I mean by that is like an operation could be something like adding 1 to a number or like grabbing information from an array. That's how we're going to measure it in amount of operations, because obviously based on different computers, things are going to run at different time. And there's a ton of different factors that affect the actual time, but we just want to get some kind of idea. Like, are we going to sit here for hours, or is it going to happen in a few seconds? And that's the main idea of BigO notation. Now, quickly before I go on, something that's important to understand is that when we talk about BigO notation, we're typically talking about very large, massive amount of information. Now, what I mean by that is, for example, if you have an algorithm that needs to run something on like 5 numbers, okay? Let's say we have like 1, 2, 3, 4, 5. Like this is our list, okay? And you need to do something with this list. Well, computers are super fast. Like they can do thousands of operations per second. So if we have an algorithm that's like pretty inefficient, but we're only taking like, I don't know, we're only using like 5 elements, like we're not going to be using that algorithm very often. Then it doesn't really matter how inefficient it is, because it's still going to happen almost instantly. You know what I mean? It's like if you write 1 line of code and it could have been replaced with like 5 that was a lot faster. Well, if we're only using like a really small amount of input, it's kind of negligible because you're saving like maybe like a millisecond, right? So it's almost just, we don't really care about small data sets. We only care about large data sets. And you guys will see what I mean as we go through here, okay? So now I'm hoping you guys have a little bit of a math background, because I'm going to start kind of just drawing some functions here and talking about growth and yeah. So what we're going to do is I'm going to draw 2 axes here, okay? And I'm going to call this my time axis, okay? And this is going to be n. Now, I haven't talked about n yet, so that's what we're going to do now. So essentially, remember how I was talking about we only really care about large data sets or like large amount of information. Essentially, we're trying to figure out, based on some kind of input, how long is our algorithm going to take relative to that input? Is it going to take like 5 times that input? Like how many operations is it going to do on that input? That's what we want to know. So our input, like if we have, let's say, an array, okay, the length of that array is going to be denoted by n. So n, you're going to see me use this a lot. This just means the length of the array. So if we have an array like this, we go from 1, comma, dot, dot, dot to n. So the length of this array is n. That's really important. That's going to be brought up a lot. So let's get rid of all of this now. This eraser is not that easy to use. Okay, there we go. So based on some kind of input n, we're going to be figuring out how many operations, in other words, like how much time is it going to take us to run. So I'm just going to draw 2 functions on here, and I want you guys just to think about which one you would rather have, okay? Keep in mind, everything we want is like super efficient, like that's what we're aiming for. Okay, so let's draw this, and let's draw a purple one that looks something like this. Okay, so we kind of have this intersection point here at this purple dot, but these are 3 different functions. Now, if you guys know anything about math, you should know what these functions might be. So for example, this function could be something like time equals n. This function could be something like time equals log of n. And this function could be something like time equals, and then maybe something like n squared, okay, like a quadratic function, which would mean it would go like that too, but we don't care about the negative side. Okay, so 3 different functions. Now I'm going to ask you, if you're running an algorithm and you want it to run as fast as possible based on like massive amount of input, which function would you take? Like, let's say these are 3 algorithms, these are how long they take. Do you want this one? Do you want this one? Or do you want this one? For how much time they're going to take, just based on their graphs, expecting that this is going to continue on to infinity, right? Which one would you want? Well, I would hope that you guys would say this purple one, right? That you guys would want this purple function, which is log n. Now, the reason you'd want that is obviously because as the size of the input increases, the time is very slowly increasing. Like, look, have a look at it here, right? So at the beginning, it increases faster than all the other ones. But once we get to this point here, it starts slowing down, and the slope is actually decreasing as we continue to go. All right, let's have a look at the red one in comparison. Well, the red one is actually way, it's faster up until this point, right? Because the time is slower. But as soon as we hit here, you can see it starts exponentially increasing, and keeps going. And this green one, well, this one's fine, but it's just a straight line. It's linear. So essentially, it increases at the same rate the entire time. Based on n, time is going to be exactly n, right? So we want this log n. Now, some people would say, though, well, what if our input size is like, let's say this is like n equals 5, okay? Let's just say that's the number. I know it's not, but let's say that's the number. Well, if we had an input of like size 3, so maybe like somewhere here, which function would you want? Well, you'd probably want this red one because the time is the shortest. But the thing is, yes, you would want that for the shorter amount of input, but as this input gets larger, you can see that this goes way faster. So that's why we really care about when n approaches infinity. So when n is like a massive number, as opposed to anything on kind of the left side of this like intersection point between different algorithms and different functions. I hope that kind of makes sense. This is the visual, right, of the speeds for our time. Okay, so we've just kind of found out now that log n, right, this is a way we're going to use BigO notation with log n as well. We'll talk about that in a second, is way faster. You can do way more operations with log n than n squared, right? Or than time n. Not more operations, sorry. It's just faster in terms of time. So these are kind of a few standard function times, like how algorithms run in these certain times. Okay, so let's now start, I guess, maybe analyzing some algorithms, talking about how we actually write BigO notation and stuff like that. Okay, so remember I said our input size is n. So n is our input. Okay, now when we write BigO notation, so we're trying to figure out how long something's going to take to run, or we know how long it takes to run. What we do is we write a BigO, we put brackets, and then in the brackets, we put some kind of function based on our n. So the function could be like n plus 1, or n plus 2, sorry. It could be like n squared. It could be log n. It could be anything like that. Now, remember how I was saying we only really care about massive inputs, right? So when n approaches infinity. Well, if you have ever done anything with limits, you'll understand what I'm about to do here. But let's say we have a function, or let's say the amount of operations that some algorithm does is like 3n plus 7, okay? Like this is the function. Like if I were to draw it, then we would have like a little grid. This would be 7. We would go like that, okay? That's what our function would look like. Now, we only care about massive input sizes. So what we can actually do is if we have a function that looks something like 3n plus 7, we can actually simplify this. And what we can do is we can remove all of the constants. Now, what are constants in this? What's a constant? A constant is something that doesn't change, that stays the same. So let's have a look at this plus 7. This is a constant. So essentially, whatever the size of n is, so like n could be infinity, we're going to do that times 3, so 3 times infinity plus 7. Now let's think about this, right? So if n is infinity, because that's what we care about, massive inputs. Does adding 7 to infinity really change how long this is going to take? Like imagine 10 billion, add 7 to it. It's still pretty close to 10 billion, right? Like that 7 didn't really make a massive difference. So what we can actually do is we can omit this 7. We can delete it. And why can we delete it? Because it's a constant. Even if the constant was something like 10,000, we can get rid of it. We can delete it. And the reason we can do that is because we only care about the input size at massive numbers. So we can get rid of those constants. All right, so now we have 3n. So what about 3? Is there any other constants left? Well, 3 is actually a constant as well. And the reason it's a constant is because it's not a variable. Like any number that's not a variable is a constant or a function. So we have 3, okay? So this is a constant as well. So let's think about this now. So what we've done is we've simplified this to 3 times infinity. Now 3 times infinity, what does that equal? Well, that actually equals infinity. Anything times infinity plus infinity divided by infinity is still infinity because it's just an arbitrary term. We don't really know what infinity is. So what we can actually do is we can remove this 3 as well. So we went from a function that was 3n plus 7 to simply n, right? So if we compared them on a grid, we would have had this one, which was that original function, and now we have a function that looks kind of like that, right? So maybe this one had like a higher slope like that, but now we have one that looks like this. Now, the reason we can do that, you're like, well, these functions are different. I agree, functions are different, but the thing is, they're both linear, meaning that as n increases, the time increases linearly, not exponentially. It doesn't grow any faster, it grows at the same rate. And that's what we care about, the rate of growth of our function. We don't really care about how, like, the exact number that it is. We just care if it's linear, if it's quadratic, if it's exponential, if it's cubic. That's what we care about. And we're going to go through a bunch of examples of different ones right now. Okay, so that's how we kind of simplify our things. We can remove the constants, meaning we don't really care about like those plus 10s or those plus 15s or the 3 times. We only care about the actual kind of variable value and what that means in terms of growth. So just the type of function, really. So let me just draw a few examples of some pretty common, like BigO notations, or some pretty common like runtime complexities. All right, so let's do a grid. And we already did the linear one, right? We already did the log, and we already did the quadratic, which looks like that, okay? These are 3 very, very common BigO notations or like runtime analysis that you're gonna see a lot. And when we start going into actually analyzing the algorithms, you guys should understand this a lot better. Okay, so those are 3 common ones, but there's 2 more that we want to talk about, and we're going to rank them in terms of like how long they take, which one is slower, which one is faster. So we did log n, but what about, Let's see, what about 2 to the n? So we did, We did n squared, but we also did 2 to the n. So who knows what's faster, 2 to the n or n squared? Well, 2 to the n is actually way, way, way slower than n squared. So this is 2 to the n, okay? And if we do n squared looks something like that. So they both grow exponentially, but 2 to the n grows way faster than n squared. So if I gave you 2 algorithms and I said alg1, well, its time, it takes 2 to the n to run. And I said alg2, that takes n squared. Which one would you pick? You'd pick n squared. Okay, so that's just important to understand because a lot of people don't know. 2 to the n, although it seems like, oh, 2 to the n is it takes a lot longer and a lot more operations than n squared. I'm going to show you an example of 2 to the n in a second as well. Okay, so there we go. So that's another example of one. Some other common ones can use more than one variable. So sometimes when we do algorithms, we might have more than one list or more than one, input, right? We could have 2 inputs. Like say we have a function and it takes 2 inputs. So let's say we have an input n1 and we have an input n2. Now a common runtime analysis for 2 inputs is something like BigO of n1 plus n2. Now, can't we simplify this any further, right? So remember I was saying like if we have 3n plus 7, we can just scratch out the 7, we can scratch out the 3, we only care about the n because that's kind of the rate of growth, right? And then I guess we can do the same thing if we have something like 3n squared. Well, we can get rid of the 3 and we'll just keep the n squared because that shows us kind of the shape of growth, which is what we care about. Okay, what if we have n1 plus n2? Well, the thing is these are different lists, right? Or different size inputs. So we need to keep both of them because this one could be like way larger than the other one. So we need to keep both of these. So whenever you have kind of 2 variables, you have to keep them both. All right, so now we've kind of talked about that a bit. I'm going to show some more advanced examples of like BigO notations and how you kind of simplify them, and then we'll actually start analyzing and hopefully it'll all start making more sense. Okay, so now I'm just going to look at a more advanced example and how we can simplify this. And remember, we really care about the shape of the function, right? So what we're going to do now is, this might be a bit complicated to you guys. You might not understand why I'm doing this, but I'm going to say if we have a function that's like 3n cubed plus n, okay? How do we simplify this? Well, first of all, you'll say, okay, we can get rid of the 3. Correct. So now we have n cubed plus n. Now the thing is, what term in here defines the growth of the function? Which one increases the quickest? Well, n cubed is like that, whereas n is just a straight line. So obviously n cubed is the faster term. So it's the more important term. It really dictates how large the input's gonna get. Like 1,000 cubed is a large number, and then you're gonna add 1,000 to it, right? So what we can actually do here is we can simplify this to just be n cubed. Now, why can we do that? Well, first of all, these are the same variable, okay? That's important to know. If this was n cubed plus like n2, so n1 cubed plus n2, we couldn't do that because n2 could be like a massive number, which would actually change this, right? So they're different variables, so we need both of them. But if we have the same variable, so n cubed plus n cubed really dictates how the function's going to grow, and that's the principal term. That's what they call it. So we can simplify this, so n cubed plus n, to just be n cubed. And that's important to understand. We're not going to, this is like a bit more advanced when you start doing stuff like this, but that's just important to understand that we really, like, this is the term that's going to dictate how fast the function grows, and that's all we care about. So we would just say this is big O of n cubed, because that's what dictates how fast it grows. Okay, so now we're done with all the drawing. Let's start getting into actually the real analysis. Actually, we're probably gonna have to still draw, but we're gonna read through some of these algorithms, which should hopefully be a bit more exciting and entertaining. Okay, so close that. So this is our first algorithm, and this is known as the linear search algorithm. And essentially what this algorithm does is it, given some input, so of size n, so in this case we're giving it a list or an array, it's gonna find a given number. So for example, here we have this list, or this array, sorry, that has how many elements? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have n equals 10, right? 10 elements. And then what we're doing is we're going to pass to our function the array and the number that we're looking for. And it's going to attempt to find this number, the index where it occurs. So what this does, it has a for loop, and it looks and it says, if we find, we'll loop through the array, if we find it, we'll log that index. So let's just first run this. You can see I've been testing them here. So I'll just call this one linear search. Okay, and you can see found at index 4. So essentially it found 32 at index 4, which would be the correct index for 32. All right, so how do we figure out the big O notation of this function? This is our algorithm, right? And we're using the algorithm down here, but this is our algorithm. How do we figure out the big O notation? Well, let's try. Okay, so this is our algorithm, obviously the stuff that's highlighted. What we want to do is figure out how long this is going to take to run in terms of n. So ARR, so this right here is n, okay? And this can change. Obviously, we could have more elements, we could have less elements. So ARR up in this parameter is going to be length of n, right? That's what we're saying. So that's length of n. This list down here is what we're passing. And what we're doing, let me undo all this so we can actually see everything that's happening here, is, you see, we're going to loop through the entire array. So essentially, we're going to say I is going to go from 0, ... to n minus 1, right? Because we're going to loop through the entire array. So if the length is 10, we'll only go to 9 because index 9. Hopefully you guys get that. So how many operations are we doing based on an input n? Well, we're going to do all of this stuff n times. So what are we doing in here, right? Because it's going to happen n times. Well, what we're going to do is we're going to log something, and then we're possibly, if we find that, we're going to break. So we're going to end the loop, right? We're going to check something, and then we're going to log something. So we could say that this is like one operation because we're checking something. We could say this is 2 operations. We could say this is 3 operations. But really, right, like we're just doing one thing on each loop. So what we would say is, well, for our input n, we're going to do one thing each. So we're going to do n things. That's what we're going to do. We're going to do n operations on our input n. So we'd say that our big O notation is of n. Now, some of you might realize, though, that we might not necessarily do n operations. Like, let's see if I erase all this, right? So we're looping through the entire array, but notice that if we find the element that we're looking for, we're going to break, which means we're going to stop looping. Now, this is another important concept with big O notation. So right now, we go to 4, right? So we're saying ARR.length, which is what, 10? So we're going to do this 10 times, so n times. But if we happen to find the element before we reach the end of the loop, we're done. We're going to break out of it, and we're not going to continue looping. So why wouldn't you say that this is big O of like a constant, like let's say 5, right? Because we only need to run that loop 5 times until we reach 32 and we end. Well, the thing is, we don't know how many times we might have to loop. In a worst case, this element 32 could have been at the end of the list, right? And in that case, it would have taken us, well, n times, n loops to find that element. So we're always looking at the worst case, which is what is the worst case that this algorithm runs in. So for example, the worst case for this is that if we have a list where 32 is at the end, that would be the worst case for this algorithm. It would take longer. Why would it take longer? Well, because we're going to break once we find the element, but if we don't find the element until it's at the very last index, then that means we had to look through the entire list. So we had to do n times, we had to loop n times until we eventually found the element. Now the best case would be if the element was at the beginning. So if we had 32 instead of 1 right here, then we would simply loop once. Well, we'd say 32 equals 32, and then we'd print it out and we would break. And that would only take one time. That'd be one operation. But the thing is, we don't know where our element's going to be because this list could change, right? This list could be any size. It could have a different amount of elements. So we're always caring about the worst case, which is big O of n, because we could at most loop n times. So it's like, it's unlikely that we'll loop n times, that it'll be at the end, but it could happen. So we need to account for that. And that's how we do this. It's always the worst case. You're never thinking about the best case. You're always thinking about the worst case. I wish there was like a clear for this, because this eraser isn't really working well. Okay, let's just close this. All right, close. Okay, apparently it doesn't want to close. So give me a second, guys. I'll try to figure this out. Okay, so I got that closed. Anyways, so that's our first algorithm, and this runs in, we'll put a comment here, big O of n, which is also known as linear time. So essentially, the longer the list gets, the longer it's going to take, and it's linear. So like if the list increases by 1, it's going to be at most one more operation we'd have to do. So this is big O of n. Hopefully you guys understand this, and we're looking at this right. It's one for loop, which means that this loop could run at most n times. Inside the loop, we do a few things if we find the element, but we really only care about how many times the loop is going to run, because that's what's going to dictate how long it takes for this algorithm to actually execute, okay? All right, so next one. That was our first one, linear search. Binary search. So you guys might have heard of this before, but essentially what this does is, given a sorted list, it's going to find, it's going to do the same thing as before. It's going to find the first occurrence of any element that we give it, and it's going to tell us where it is in the list. So let's just run this first of all. So if I say, by the way, I'm just using Node.js to run this stuff. I don't know if you guys care, but anyways, we'll do binary search JS, and you can see it finds one at index 0. If I change it to be like 8, I should find one of these 8s for us. So let's run this, and you see it finds it at index 9. And I mean, you can count the index if you don't believe me. So essentially it just finds the element. But the thing, why is this different than this? They do the same thing, right? Given an array and given a number, they tell us where that number appears. Why is this different? Well, this runs a lot faster than the last algorithm. And why does it run faster? Well, we're gonna talk about this right now and how this works. So this is known as the binary search algorithm. And why it's called binary is because every time it runs, it decreases the size of our list. And you guys will see how this works in a second. So essentially what this does is it looks at, we looks at the middle index of our sorted list. And think about it, if you have a sorted list and you're looking for some kind of element, so we're going to look at the middle index and we're going to determine if that middle index is greater than or less than the element. So in this case, we're looking for 8, okay? The middle index in our list would actually be, okay, let me change this to be like 10 so it makes more sense. So we're looking for 10, okay? The middle index in our list would be something like 8. So we know this list is sorted, meaning it's going from least to greatest. So if we look at the middle index, which is 8, we say, well, is 10 greater than or less than 8? Well, 10 is greater than 8, which means that we know that 10 cannot actually be in this left half of the list or the array. Why can't it be there? Well, because it's sorted, and if 8 is the middle and 10 is greater than 8, there's no way it can be behind 8. So why would we bother looking at any of these elements? Well, we wouldn't, and we're not going to. Okay, so let's say we cut that portion of the list, right? So the highlighted portion we're no longer looking in. And now what happens is our list turns into this, the highlighted portion. We have 8, 8, 9, 9, 9, 9, 9, right? And we're still looking for 10. So what we're going to do is now our list is simply this, and just this part with the brackets. So we're going to do the same thing we just did, except with this list. We're going to find the middle index of this list, which in this case would be 9. And we're going to say, is 10 greater than or less than 9? And again, 10 is the element we're looking for. We say, well, it's greater than 9, which means that all the elements to the left here are gone. We can remove them. So our new list becomes this. And now we say, well, why would we bother looking at this portion when we know it can't be there, right? So now we have this list. And now what we do is we look at the middle index. In this case is 10. And one of our checks is it greater than, is it less than, or is it equal to? And we find that 10 is equal to 10. We know what this index is, and we return that to our, from our function. So that's how the binary search algorithm works. So now let's try to figure out how many operations this takes. So let's bring up our drawing thing here. Or that's not the one I wanted. Sorry, 1 second. I want this one. And let's dissect this, okay, right? So we have a list. Let's say we have a list of like 1, 2, 3, 4. And every time we run this loop, right, every time this runs, so the while loop here, which is right here, we split the list in half. So our first loop, we look something like this. Our second loop looks something like this. And our third loop would look like this, right? Because every time we essentially cut off half until we get down to one element. And the worst case for this algorithm is that we look through every single possible, like we look through the entire list until there's only one element left. And then if there's one element left, it's either the element we're looking for or the element doesn't exist that we're trying to find, right? That's the worst case for this algorithm. Because technically, like say we pick the middle index of 2, and that's equal to what we're looking for, like so let's say we're looking for 2, then we'll just return that index right away. So it could happen faster than possibly splitting it up all the way. Okay, so we split this up, and then we're left with this. So our input size was 4, right? Okay, but we only ran at most 3 operations. Really only 2, because this, like the first operation brought us to this. So we really only did 2 operations. This is operation 1, this is operation 2, right? We just ran the loop 2 times. Loop ran 2 times. So what is that actually equal to? Well, I want you guys to figure it out. So I'm going to do one more example, okay? So let's increase this list now to be 5, 6, 7, 8, okay? So now we've just doubled the size. So it was 4, so it was to there, but now we've doubled the size and we've added those. What operations do we do now? So we start and we split the list in half. So we're either going to take the left side or the right side. So I mean, we can pick, it doesn't really matter. We'll say we take the left side. So now we're at 1, 2, 3, 4. Okay, now what do? Split this list in half again. 1, 2. What do? We split it and we get 1. So notice that now we have 1, 2, 3 operations. We doubled the size of our list and we only added 1 operation or 1 more run of this while loop. Okay, because this is what this while loop does essentially. But how does that work? Well, or what function is this? We talked about it. This is actually log base 2 of n. And what that means essentially is based on whatever the size of our input is, we can find how many operations at most will run by doing log base 2 of n. And log base 2 of n is a function like this that actually decreases in slope as n gets larger. So this is a super fast algorithm, right? And we would want to use this if we want to find something in a massive list. The only disadvantage of it is you need a sorted list. Otherwise, you can't really do something like this, right? If you don't have a sorted list. And that is essentially how it works in terms of binary search. And that's why it's log base 2 of n. Now I want to talk about quickly, I really wish there was a clear thing for this, man. So I could, all right, well, that's fine. It's flawed in the app. Maybe I'll make one myself. But what we do here, right, is like these are all the operations that could run each while loop, right? So every time we loop through, like this while loop essentially is going to happen at most log base 2 of n times, okay? But we do like a bunch of different operations in this while loop. Like let's say we do this, let's just say we do like 5 operations every time it loops. Well, wouldn't you say that that's like 5 times log base 2 of n? Well, you'd be correct. We do 5 operations log base 2 times, right? Because this happens log base 2 times, or of n, sorry. But we do 5 operations. But the thing is, 5 is a constant, right? And we don't care about constants, so we just remove it. And we say that this is then big O of log base 2 of n. And that's how that works. Okay, so we'll go a bit faster now for these next ones. So now we're going to example 1. And this one is just one that I wrote myself. And essentially what it does is it counts duplicate elements. So let's try to analyze this and figure out how long this is going to take. So the important thing to look at when you're analyzing something is the amount of loops, right? Because remember, we don't care about the constants. So all the stuff inside of these loops, it doesn't matter how much you're really doing because we're just going to omit the constants anyways. Like say you're doing something like n times, but you do like every n you do 5 things, that's 5n. Well, you just get rid of the 5. So we don't care about the constants, right? So how many times does this happen? We're going to count the duplicate elements. So essentially given some kind of array, we're going to find how many elements appear more than once. So for example, like this one, there's 2 duplicate elements because 2 is duplicate and 6 is duplicate. Even though there's like 3 2s, just because 2 appears more than once, like that counts as once. You know what I mean? Like it's a duplicate element. That's what we count. So I mean, I'll show you that this works first. Didn't mean to close all that. Example 1. Okay, and you see that we get 3 duplicate elements, and that's because 77, 6, and 222, right? So how long does this take to run? Well, let's look at it. So what we're doing is we're looping through the array.length, okay? So that's going to happen what? N times, right? Because array, the length of our array is n. That's our input size. This is length n, whatever that length is. So this is going to happen n times, this first for loop. But then inside of that for loop, what do? We loop again n times. We say we're going to loop again through the entire list. So we're looping once, and then every time we loop once, we're looping through the entire list again. So essentially, every one of these for loops, we're looping n times. So every time that this runs, we loop n times again. So this runs n times, but this runs n times, and this runs every time that this runs. So we say that this runs n times like that, and this runs n times, but since this for loop is inside of the other one, it means that every time that this runs, this is going to run. So you might be seeing what I'm getting at here. How long does this take to run? Well, this actually runs in n squared. And why does that happen? Well, because for every n, we do something n times. So essentially, that's n multiplied by n. And n by n is n squared. So this is quadratic. And as the length of our input increases, this is going to take a lot longer to run. These are things we want to avoid, is embedded for loops and embedded while loops, because, well, it takes a really long time to run. And if I were to put another for loop in here, like this, and say it does something, well, then this would run, if it ran n times, right? So this runs n times, this runs n times, this runs n times. So we're going to run n cubed times, which is a crazy amount of times to be running, right? So that's how we kind of do that. So I think that one's pretty straightforward. I don't need to really do too much for that. Okay, so let's go to example 2. Example 2, okay, so all this one is doing, and it's similar to the last one, is we're just going to print x, y, z. And this is a good example. Actually, I don't want to print it yet because it's going to give it away. But what we do is we take 3 variables, so like a, b, c, as our input. And what we're going to do is we're going to loop a times, b times, and c times. Okay, a, b, c times. So this one's a bit more complicated, actually. What's the BigO notation of this? How long does this take to run? Right? So we can say a, b, and c is like our n, like our input, how long it's going to take to run. Well, what we do is we run a times, and we run b times a times. I know it's confusing, but we run this for loop, b times every a time. So that's a times b, right? So we run these 2 for loops, a times b times. Now, what about this third one? There's another for loop inside of another for loop. So this runs c times. So every time b runs, this runs c times. And every time a runs, this runs b times. So this is actually a times b times c. Now, what can we simplify it to be like n cubed? Well, you can't, because they're 3 different variables, right? If it was one variable and it was like a, then we would say a cubed, because it's a times a times a. But since it's 3 different variables, we say this runs in a times b times c. And I'll prove it to you. So I'm going to run this now, example2.js, and watch my screen, okay? So we get a bunch of output. Let's scroll through it. So these lines of code ran like this many times, and you'll see. So we have x starts at 0, y is 1. X is 0, y is 1, z is 1. X is 0, y is 1, z is 2. X is 0, y is 1, z is 3. So you see that essentially z goes 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and that runs a ton of times. Whereas x stays at 0 and goes to 1, goes to 2, goes to 3, and then once it's done, it's done. So this kind of gives you an idea of exactly how this works, right? So you go x0, y0, 0, 0, right? And then y will change to 1, and then z will change, right? And that's exactly how it works. So that's how we can kind of determine that this runs a times b times c times. And I mean, if you wanted to count these amount of inputs, you would get 5 times 5 times 5, which is essentially 125 lines, okay? That's how long that runs. I don't want to close that. Okay, example 3. So this one, this one actually is going to generate all of the binary numbers that are of length 16. So it's going to start from 0 and go to length 16. So all of the binary numbers that are of length 0 to length 16. Does anyone know how many numbers that is? It's a lot of numbers. I'll tell you that right now. Now, this works using something called a queue-based algorithm. I'm not going to explain what that is because it's a bit confusing, but essentially, I'll run the program and then let's try to figure out how long this runs in, okay? So let's go down here. It's example3.js. All right, ready? I'm going to run this. Watch my screen. This is going to take a second to happen. And this is what I'm talking about with the time complexity, right? I'm only making all of the binary numbers that are of length 16. But look how long this is taking to run. And if we didn't know anything about time complexity and we weren't printing this out to the screen, we would not probably have realized how long this algorithm that I created takes. It's super inefficient, but it's really the only way to generate all of these different numbers. So you can see, I mean, if you scroll through, we have a ton of different binary numbers. I can't even reach the end, the last input, like the start one. So this, how long does this take to run? Well, this actually takes 2 to the n. 2 to the n times, where n is essentially like the length of the binary number, which is going to be 16 in this case, okay? Because that's how many possibilities of binary numbers there are, 2 to the 16. And I mean, we can prove that pretty straightforward. I'll draw this to you if you guys know anything about binary. Don't want to use that. I want to use this, right? So binary numbers, you can either be 0 or you can be 1. It's 1 or 2. And they can obviously have like an infinite length. So we're doing all the binary numbers of length 16, which means that we can, well, I'm not going to draw them all out, but let's do an example with 3. So if we have 3 digits for a binary number, then we can have 0, 0, 0. We have 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, and then this goes 1, 0, 0, 1, 1, 1, no, 1, 0, 1, sorry. Why is this so difficult to do? 1, 1, 0, and then 1, 1, 1. So we have 1, 2, 3, 4, 5, 6, 7, 8 different binary numbers for 3 digits. Okay, for 2 digits, like let's just scrap, what row should we scrap? Okay, let's scrap this row, all right? And then have a look, like these 0, 0, 0, 0. So these are all the same as the ones above. So we get 4. So for 2 digits, we get 4. For 3 digits, we get 8. For 4, we get 16. And we essentially get 2 to the amount of digits. So in this case, we get 2 to the 16. So that takes a really long time to run, right? Our input size was only 16 because we're only doing 16 digits. But 2 to the 16 is a massive number. And that's why it took us so long to run that program. So, if we had an algorithm that could do that in linear time, then we would only have ran it 16 times, and that would have happened instantly, but it was happening in 2 to the 16, which means that it took a long time, and that's another reason, obviously, we need to understand time complexity and how long these things are taking. Now, again, notice, right, like I'm doing all of this stuff in this loop. Like I'm doing 1, 2, 3, 4, 5, 6, 7, 8 operations every loop, and this loop is going to happen, well, 2 to the 16 times, okay? This happens 2 to the 16 times, multiplied by, how many operations is this? 8. Now here's the thing, right? Like 2 to the 16 is a massive, massive number. Multiplying it by 8, yeah, it makes it 8 times larger, but really, like, we can just neglect this because it doesn't really tell us anything more about the shape. We know the shape is exponential and it's happening like taking a really long time. So by multiplying it by 8 doesn't really give us much value. It just kind of tells us it's 8 times larger. It doesn't tell us the shape of the increase, which is what we care about. We just care about the shape of the increase, okay? So that's kind of it for that one. What was the other example I did? Okay, so this is one with 2 input variables we're going to talk about now, how we do this. All right, so we have array 1 and array 2. Now, how do we do this with 2 input variables? Well, essentially what we do is we just say, we're going to look at the first for loop, we're going to look at the second for loop, and then we'll just see what happens in here. And this first for loop, well, what does this run in? Well, this runs in length 1, okay? So like array 1 has length of n1. Array 2 has length of n2. So this first for loop is going to happen, what? n1 times. And this for loop, the second for loop happens n2 times. But it happens every time that n1 happens. So we say this happens, n1, this happens n2. So since this for loop's inside of the other for loop, we simply say this is happening in n1 times n2 time. In other words, big O of n1 times n2, and that's how we determine that. So this runs in n1 times n2, and the reason we can't just simplify this is because obviously these variables are different, and if this list was like way bigger than the other one, it would affect how long it was going to take. So yeah, so that has kind of been it for BigO notation introduction. I hope that you guys at least have some sense of kind of the speed of some different algorithms, how you can kind of look at them and get a very brief idea of how long they're going to take. This is super useful, and I highly encourage you guys to be critical of yourself if you're writing efficient code or not. If you're writing code that runs in n squared, just know it's going to take a long time to run, right? If you're writing something like this that happens in 2 to the n, understand that that's going to take a massive amount of time to run. And if you're writing something like binary search, you're going to be like, well, if I have massive lists, it might make sense to use a binary search on them because it's going to be so much faster to find elements, right? So as I wrap up this video, just a reminder that this video was sponsored by Microsoft. If you're not already, you guys should head over to their YouTube channel and hit subscribe. And remember to check out Dev Collective in the link in the description. A ton of awesome courses completely for free. I know you guys are going to find a lot of value from that. So with that being said, thank you guys for watching the video, and I will see you again in another one.